So next we're going to talk about probably the largest source of distributed energy resource in the United States, and other than hydroelectric, definitely the largest source of renewable energy in the United States, which is wind. So wind energy, sometimes people just call it wind power. It's the process by which the wind is used to generate mechanical power, and then that mechanical power is turned into electricity. Wind turbines convert the kinetic energy in the wind into mechanical power, and this mechanical power can be used for specific tasks. And historically, it's been used for grinding grain or for pumping water. In modern times, we use the mechanical power in wind to turn a generator that converts this mechanical power into electricity. So the I've got just a picture of a modern wind turbine in case you haven't seen one. But more importantly, I think, is the diagram over here, which illustrates the major components of a wind turbine. We've got some sort of tower that's typically made of, in this case, tubular steel. These towers can be made of concrete. They can be steel lattices. And the point of the tower is to support the structure of the turbine located at the top of it. Because wind speed increases with height, taller towers enable turbines to capture more energy and generate more electricity. Atop the tower is what's called the nacelle. The nacelle sits atop the tower and contains the gearbox, low and high speed shafts, a generator controller, and a brake. Some nacelles are large enough for a helicopter to land on. Other ones are no bigger than, a barrel of oil or something like that. So inside the nacelle, we've got the rotor assembly. It contains the blades here and the hub that is free to spin. The blades here, they're going to lift and rotate when the wind is blown over them, causing the rotor assembly to spin. Most of these turbines are going to have either 2 or 3 blades. There's a pitch system that is used to turn the blades out of the wind to control the rotor speed and to keep the rotor from turning in winds that are too high or too low to produce electricity. Also shown here, a brake can be used to stop the rotor mechanically, electrically, or hydraulically in emergencies, depending on what type of brake that they have installed there. There is what is called a yaw drive system, and a yaw drive, which is powered by a yaw motor, orients turbines to keep them facing the wind if necessary for when the wind direction changes. So the purpose of this is to kind of rotate the nacelle. The yaw motor rotates the nacelle. This is for an upwind turbine, as we'll see in a minute. Downwind turbines, which is a different structure, they don't require a yaw drive because the wind manually orients the rotors. Here we see that a gearbox manually connects the low-speed rotor shaft to a high-speed shaft, and the purpose of this is to increase the rotational speeds of the rotor from 30 to 60 RPM to about 1,000 to 1,800 RPM for the electric generator. This 1,800 RPM typically is the rotational speed required by most small generators to produce electricity. This gearbox is a costly and heavy part of the wind turbine, and engineers now, probably by the time you watch this, engineers will have been even more exploring direct drive generators that operate at lower rotational speeds and don't need these gearboxes. This generator clearly is going to produce a 60 cycle AC electricity, and typically it's some sort of off-the-shelf induction generator. An electrical controller is, let's see, the controller located at the back here uses sensor data to start up the machine at wind speeds of about 8 to 16 miles per hour, and it's going to shut the machine off for safety reasons at about 55 miles per hour. Turbines do not operate at wind speeds above 55 miles an hour because they may be damaged by these high winds. These modern wind turbines, although I showed what's called a vertical axis wind turbine, a horizontal axis wind turbine, HOT. There are other designs, and modern wind turbines will fall into 2 basic categories: the horizontal axis variety, or a horizontal axis wind turbine called a HOT, and the vertical axis design, the vertical axis wind turbine called a VOT. So this is a HOT, H-A-W-T, and this is a VOT, V-A-W-T. Horizontal axis wind turbine, that means the wind blows along the horizontal axis of the turbine, or the rotation is along the horizontal axis of the turbine. And VOT is a vertical axis wind turbine, meaning the axis of rotation that the wind causes rotation about is along the vertical direction, right? This one is an egg beater style Darius rotor. The primary advantage, or why Vaught's have been used, is that no yaw control is necessary to keep them facing into the wind. A second advantage is that the heavy machinery that's typically located in the nacelle is now located on the ground, which is very nice. Why? Well, we can more easily service this, and it results in less construction cost, and we don't have the necessary tubular steel tower to support the heavy weight of all this. Additionally, the blades of a Vaught design are in constant tension. You'll notice that they're fixed at both the top and the bottom, and they don't have to handle the bending stresses that are associated with the constant flexing experienced by Haught designs. Right? So clearly the wind blows on these things are subjected to flexing forces, whereas since these are fixed at both ends, that isn't as much of an issue. Unfortunately, the design advantages of reduced costs at the bottom, constant tension, making the blade design a little bit more simple, these advantages are overshadowed by the major disadvantage of the vertical axis wind turbine. The blades have to be located near the ground where wind speed and thus available wind power is lower than at high altitudes, and prevailing winds are more turbulent and less predictable in duration and speed at low altitudes. So, although this design works better, the characteristics of wind at the surface of the Earth is less desirable to produce electric power, and we don't use them very frequently at all. Therefore, as you may have already guessed, if you've ever driven around the state of Indiana, Haught designs dominate the wind market. And third kind of concern is that I can adjust the angle that these blades face into the wind. I can't do that with a Vaught design, so I can't control the pitch of my blades to shed excess wind and to control rotor speeds. So I don't have that element of control in the Vaught design in controlling rotor speed as I do in the Haught design. Due to the deficiencies of the Vaught design, almost all modern wind turbines are of the Haught design and are produced in two categories, which I've shown here: the upwind Haught and the downwind Haught. So we've got the upwind here, and we've got the downwind here. By far, the vast majority of wind turbines have an upwind design, as shown here. Upwind machines have the rotor facing into the wind, as we see here. This arrow, it's a little hard to see that direction, but this arrow points wind flowing in this direction. Upwind machines have the rotor facing the wind, the advantage being that they avoid wind shade of the tower. What that means is that this tower is going to block wind. If you were to be small enough to stand behind the tower, you would experience reduced wind. Well, if a blade is behind the tower, it will experience reduced wind. This effect is called wind shading. So wind shading is the effect of the tower blocking some of the wind. Upwind designs reduce this effect. There is still some effect because there is this pole blocking the speed at which winds in this plane can propagate, so there is some sort of reduction effect. So it's not completely eliminated, but it is reduced. The major drawback of this upwind design is that the rotor needs to be made rather inflexible and placed at some distance from the tower, because under high wind speeds, these blades are going to bend and they're going to flex, and if they flex enough, they'll make contact with the tower, right? It'll spin and they'll hit the tower. So these things have to be inflexible to avoid that, and then also they have to be located a pretty significant distance away from the tower itself. In addition, an upwind machine needs a yaw mechanism to keep the rotor facing into the wind. The wind is going to want to push the nacelle as the wind blows past it, and so we have a motor that always orients this to face directly parallel into the wind direction. We got to face it directly into it. Downwind machines have the rotor placed on the lee side of the tower, or the downwind side of the tower. They have the theoretical advantage that they don't have to have a yaw control because the wind will just auto-orient them under normal rotation. If the rotor and nacelle have a suitable design to allow them to passively rotate. A more important advantage of the downwind design is that the rotor can be made more flexible, which because the bending direction is going to be away from the tower in this case. So this will reduce weight and will also take a significant part of the load off the tower when the blades bend in high winds. The major drawback of this is the fluctuation in wind power due to the rotor passing in front of the wind tower and due to the effects of the wind shade of the tower. This may give more fatigue loads on the turbine than with an upwind design. The effects of the tower shadowing may to some extent be reduced by utilizing a tower design which provides minimal obstruction to the flow, so very narrow towers can reduce this effect in the downwind design. The next feature you'll notice is that I've shown that one of the turbines has 3 blades and one has 2 blades, which are kind of the 2 most common configuration. I do not mean to imply that upwind designs have 3 blades and downwind designs have 2 blades. That's not the case. You can have 3 blades on a downwind design, you could have 2 blades on an upwind design. But the number of blades on the wind turbine affects the torque and speed relationships of the machine. Multi-bladed designs present a large area of rotor that's facing into the wind, enabling both high torque and low speed operation. As the RPM of the turbines increase, the turbulence, though, caused by one blade will start to affect the efficiency of the following blades. Therefore, with fewer blades, the turbine can spin faster before the interference from turbulence becomes excessive. Faster spinning blades result in a generator that can be physically smaller in size. So many blades, I can have low speed, low torque, but I need a big generator. Few blades, and high speed operation is physically limited by turbulence. Low number of blades, the turbulence is reduced, therefore allowing me to spin at higher speeds. Smaller overall generation generators can therefore be used. These trade-offs has resulted in most wind turbines having either 2 to 3 blades, although I personally have actually seen a one turbine construction previously. Wind turbines can be built on land or offshore in large bodies of water like oceans or lakes, though the United States does not currently have any offshore wind turbines that are producing electricity for the grid. Utility scale turbines range in size from 100 kilowatts to as large as several megawatts. And these larger wind turbines are more cost effective and are typically grouped together to form wind farms, which provide bulk power to the electric grid. Single small turbines below 100 kilowatts are used for homes, powering remote telecommunications dishes or water pumping. Small turbines are sometimes used in conjunction with diesel generators, batteries, and photovoltaic systems, and these systems are called hybrid wind systems and are typically used in remote off-grid locations where connection to the utility grid is not available. This is a National Renewable Energy Lab map of current installed wind power capacity across the United States. You'll notice that it's color-coded, dark green being the most amount of wind power. Clearly, you see Texas dominates the wind market in the United States. This is in megawatts. Almost 13,000 megawatts of installed wind power capacity in Texas alone. Indiana, we're not too bad here in Indiana. We're at 1.5 thousand megawatts. That puts us kind of in the higher end of the United States. We'll notice our neighbor to the south, Kentucky, no installed megawatts. But if you add all this up, you get about 62,300 megawatts of installed wind capacity. Remember, like hydro, wind will get derated depending on availability of the wind supply. So these tend to be located on ridges or corridors where large amounts of wind are available to you. We're not going to go into it in this class. You can find wind maps. The National Renewable Energy Lab has conducted wind studies. They can show you what prevailing wind conditions are basically across the United States. You can know what direction, what speed, and with what frequency the winds blow, and you have access to that data pretty regularly, pretty easily from the Department of Energy in modern times. I don't think there's anything else that I wanted to touch on wind capacity here. Okay, so now what we want to do is a similar calculation for what we did for the hydroelectric resource, but now we want to turn to available wind power. So wind power is based on kinetic energy. And we know the formula for kinetic energy is Ke, just our symbol for kinetic energy, is equal to 1/2 mass times velocity squared. Very well-known physics 1 formula, 1/2 mv squared or mv squared over 2. So if we take this and we say, well, what's the power of the mass of air moving at a velocity v through an area A? It's therefore power is equal to energy divided by time. So we get 1/2 mv squared. The mass of the air moving through the area times the velocity of that area squared. We divide that by time. Now we're just going to be doing a little bit of rearranging. We get 1/2. I'm going to write this as mass over time times velocity squared. And this is equal to 1/2, and I'm going to introduce a new symbol. It's a thermodynamic symbol, m dot v squared. In this equation, m dot is called the mass flow rate, or how much mass moves through a given area per unit time, right? So if I've got a cross-section of a wind turbine, it's how much mass of air flowed past that cross-section of a wind turbine in 1 second, right? So this mass flow rate, in turn, is calculated as the product of air density, air speed, and cross-sectional area. So we say m dot, or the mass flow rate of air passing through a turbine, is what's the density of air, rho, first. What is the area through which the air is flowing, or the cross-sectional area of the rotor blades of the turbine, A, and then we multiply it by the wind speed, or the wind velocity, V. So if we combine this equation for the mass flow rate with this equation for power, we end up getting the power stored in the wind is equal to 1/2 density of air times cross-sectional area of the rotor blades times velocity cubed. So 1/2 rho AV cubed. So again, P sub W, it's the power of the wind. It's in watts. Rho is the air density, just like water density. It's measured in kilograms per meter cubed. A is the cross-sectional area through which the wind passes. It's a cross-sectional area, so that's in meters squared. And V is the wind speed, which is perpendicular to A, and it's in meters per second. From this equation, we can see that the power stored in the wind is proportional to the cube of the wind speed, indicating that if we double the wind speed, we increase the available power, P sub W, by a factor of 8x. The equation also tells us that the available power is proportional to the area of the turbine rotor that is normal to the wind, A here. For a conventional horizontal axis turbine, the swept area of the turbine is circular. The cross-section of the area is circular, so the area of that is given by pi r squared, where r is the length of the rotor blades in this calculation right here. We can therefore see that doubling the length of a rotor blade increases the available power by a factor of 4 times. For these reasons, it is proven economical to build large, tall wind turbines, just driven by this formula right here. Larger units have longer rotors, and taller units locate the rotors higher in the atmosphere for where wind speeds are higher than at the Earth's surface. However, there's a limit to how much power can actually be extracted from the wind by a rotor, and it's related to the maximum rotor efficiency. When wind approaches a turbine, it is slowed down as a portion of its kinetic energy is extracted from this turbine. The wind leaving the turbine on the lee side has a lower velocity and reduced pressure, causing the air to expand downwind of the machine. So if we draw the shape of the air mass that passes through the turbine, this is called a stream tube. We see that we've got a stream tube. As the air is slowed down when kinetic energy is extracted from it, its speed decreases and its volume increases. So we get this kind of like Coke bottle looking shape called a stream tube. If we were somehow able to extract all the kinetic energy from the wind as it passed a turbine, the kinetic energy of the wind would become 0. If we take all the energy out of it, the kinetic energy on the lee side would have to be 0. and therefore, since it still has a mass from the Ke equals 1/2 mv squared formula, its velocity would be 0, i.e. the wind would stop moving on the lee side. This mass of air in turn would prevent any more wind from passing through the rotor, and therefore the downwind velocity of a wind turbine cannot be 0 kilometers per hour. Therefore, when extracting energy from wind, the downwind velocity has to be slower than the upwind velocity. There has to be a speed reduction, but we can never go to 0 on the lee side in terms of downwind speed. In this figure, let's let V equal the upwind velocity and Vd equals downwind velocity. So V equals upwind velocity and V sub d is just the velocity of the air downwind. The power extracted by the rotor blades is going to be based on the difference between the power in the upwind velocity and the power in the downwind velocity. So power, remember, is just equal to 1/2 mass flow rate times velocity squared. So the power extracted by the rotor blades is going to be 1/2 mv squared minus 1/2 mvd squared, or PB is equal to 1/2 the mass flow rate, m dot, times the v squared minus v sub d squared. So we can most easily determine the value of the mass flow rate, m dot, in this formula in the plane at the rotor. At this point, we know the cross-sectional area of the rotor. It's just the swept area of the rotor blades. And we can determine the mass flow rate at this point from m dot equals the density of the air times the cross-sectional area of the rotor blades times Vb, which is the velocity of the wind at the wind turbine interface, Vb. So this, again, Vb, is the velocity of the air measured exactly at these rotor blades. It's slower than the upwind speed, but faster than the downwind speed. How fast is it? Well, we could make a simple estimate for Vb. We could say that we could estimate Vb is equal to, well, maybe it's the average between the two, V plus Vd over 2. Right? That seems like a very simple estimate, and it is a simple estimate. There are more sophisticated estimates for determining Vb, but for a first approximation, this is a pretty good one. And so what we're going to do is we're going to take our estimate for Vb, and we're going to insert it into the equation for power extracted from the rotor. So we get 1/2 density times cross-sectional area. We now multiply by Vb, which is V plus Vd over 2. Trying to make it all fit. V plus Vd over 2. And then we need to multiply by V squared minus Vd squared. Right? We have 1/2 m dot is rho a Vb, where Vb is V plus Vd over 2, so that goes here. And then I don't have room on this, so I'm just going to say this term gets inserted right there still, V squared minus Vd squared. So we've got the power extracted by the blades is equal to 1/2 air density, cross-sectional area swept out by the rotor blades, times V plus Vd over 2 times V squared minus Vd squared. So we see that there's terms V squared, Vd squared, V plus Vd. So what we're going to do is just a little bit of algebraic manipulation. I'm going to clear my slide off right there. And algebraically I get that the power extracted by the blades, I'll just rewrite our previous equation. It was 1/2 rho a, and then we got V plus Vd over 2, which was the our estimate for wind speed at the blades. And then we need to multiply that by v squared minus vd squared. So we can manipulate this. What we're going to do is just a little algebraic manipulation gives us 1/2 rho a v cubed right? We need to multiply that by 1/2 times 1 plus vd over v. And then we need to multiply that by 1 minus the quantity, vd over v squared. And what we'll notice is that the 1/2 p av cubed is just the power contained in the wind. So that PB, the power extracted by the blades, is power in the wind, 1/2 PAV cubed, multiplied by this whole term here, which is 1/2 times 1 plus VD over V times 1 minus VD over V squared. I left off a parenthesis on that one. So we've got this formula. Why do we do this? So I've just retyped that here. And what this tells us is that the power extracted by the blade is the power contained in the wind times some factor that is dependent on the difference between the downwind speed and the upwind speed. So what we can do is we can find the maximum rotor efficiency by taking the derivative of this term right here. So let's do this. Let's let VD over V equals X. So this is going to become, we're going to call this C sub P, and it is equal to 1/2 times 1 plus X times 1 minus X squared. Let's see, 1/2, yep, that's correct. So what I want to do next is I want to take the derivative of CP with respect to X. That's just d CP dx. Why am I doing this? Remember, in a function, if I take the first derivative, I can determine if it is a local max or min. So that's the test that I'm using. I'm taking the derivative of this function right here. I'm finding where it has a zero crossing. That gives me a local maximum, right? So I take this. Let's just take the derivative. Remember, the derivative, the chain rule, the derivative of the first times the second plus the derivative of the second times the first, right? So we pull out the constant is our first action, so 1/2. Now we need to take the derivative of 1 plus x with respect to x. That is just 1. The derivative of the first times the second, which is 1 minus x squared. Now we need to add to that the derivative of the second, which is just, the derivative of this is minus 2x times the first, which is 1 plus x, right? I set that whole equation equal to 0, and I need to solve for x. If I solve this equation for x, I find x is equal to 1/3. So that gives me the maximum for this function is 1/3. So that's equal to VD over V. So what this is telling me is the maximum efficiency of a rotor is achieved if we can design our rotor such that the downstream wind speed is 1/3 that of the upstream wind speed. If we substitute this result into the equation for C sub P here, we find that the maximum CP max, it occurs when the ratio of VD over V is 1/3, so I just say 1/2 times 1 plus 1/3 times 1 minus 1/9 That's 1/3 squared, right? That gives me about 60%, 0.059. So we find out that due to this relationship here, the maximum efficiency of a perfect wind tower is limited to about 60%, and that is achieved when I design my tower such that the downstream wind speed is 1/3 of that of the upstream wind speed. Although the theoretical upper limit of wind turbine is limited to about 60% of the power contained in the wind, modern turbines under best operating conditions are only approaching about 80% of this limit, which makes them overall 40 to 50% efficient at converting wind power into rotational power. For a given wind speed, rotor efficiency is a function of the rate at which the rotor turns. Rotors that turn too slowly let too much wind pass by and efficiency drops. Rotors that turn too fast will cause blade turbulence that increasingly affects the following blades and decreases overall efficiency. To quantify this, rotor efficiency is calculated as a function of what's called the rotor tip speed ratio, or TSR, which is the speed at which the outer tip of the blade is moving divided by the wind speed. So we have a formula called TSR, right? And it is, again, the tip speed ratio, and that's equal to rotor tip speed and we divide that by wind speed. And that is, it's going to be, rotor tip speed is RPM rotation times pi times the diameter of the rotor. Having a little problems at the end of this guy here. And then I divide that by 60 times the wind velocity is the formula that we're using. So RPM is the rotor speed in revolutions per minute. D here is the rotor diameter in meters. V is, again, the upwind speed of the turbine. It's in meters per second. We can see that from, whoops, erased it, sorry about that. American multi-blade systems have a TSR of approximately 0.8, which results in an overall efficiency of about 30%. 2 and 3 blade rotor systems can spin much faster with TSRs of 3 to 7, max efficiencies up to about 50%. So let's apply this concept of TSR to an actual example. We've got a 40-meter, 3-bladed wind turbine. It's producing 600 kilowatts at a wind speed of 14 meters per second. We're going to assume the air density to be 1.225 kilograms per cubic meter. At what RPM does the rotor turn when it's operated with a TSR of 4? What is the tip speed of the rotor? If the generator needs to turn at 1800 RPMs, what gear ratio is needed to match the rotor speed to the generator speed? And what is the efficiency of the complete wind turbine under the conditions that we've got stated here? So remember, our equation for the TSR is just equal to RPM times pi d hopefully that's a little more legible than the last slide. We divide it by 60 times the upwind speed, 60V. So what this says to us is that TSR, which was 4, is equal to our RPM, which is what we're trying to solve for. We need to multiply that by pi. We had a 40-meter system, so we need to multiply by d, which is 40. And then we need to divide by 60 times the upwind speed, which we were told was 14 meters per second. Right. So that gives us a RPM of 26.7 rotations per minute. RPM, rotations per minute. We've got that conversion is built into this formula. So remember that this is the calculation of TSR, but the definition of TSR was rotor tip speed over wind speed. So TSR is also equal to rotor tip speed over wind speed. And so a TSR of 4 just tells us that the rotor tip speed is 4 times the wind speed, right? So we just need to multiply, 14 meters per second by 4. That gives us 56. So I'm going to call it rotor tip speed. That's equal to 14 meters per second times the TSR, which was 4, so 56 meters per second. So that tells us how fast. That's about 125 miles an hour. So we've got a RPM of the rotor of 26.7 RPM. We need a generator. It needs to turn at 1800 RPM, so what's the gear ratio? So the gear ratio is just the ratio of the two speeds. Gear ratio is going to be the generator RPM divided by rotor RPM. We'll call it RPM sub generator over RPM sub rotor. So that's 1800 revolutions per minute. And we divide that by our 26.7 RPM. So we need a gear ratio of 67.4 for this system. The next part of the equation asked us to determine the efficiency of the complete wind turbine under these conditions. So what's the efficiency of the complete wind turbine under these specified conditions? So to calculate that, we're going to turn back to our power in the wind formula, PW. Remember, that's 1/2 air density cross-sectional area of the turbine times the velocity cubed. That's the power stored in the wind. So that is 1/2. We were told air density is 1.225 kilograms per cubic meter. That's meter cubes there, 1.225. It's a really hard to read kilogram, but that's what that is. We need to then multiply that by cross-sectional area, which is pi r squared. 40 meters over 2 to get radius. So that's 40 meters divided by 2 gives a and then I need to multiply that by velocity cubed. We were told the wind velocity was 14 meters per second. That need to cube that. I get a total power contained in the wind of 2,112 kilowatts. The efficiency of that system, we were told what the output power was. It was a 600 kilowatt system, so it's P out over Pn. We get 600 kilowatts divided by 2,112 kilowatts. Right? And so that gives us an efficiency of 28.4%.